Hello. So in the previous lecture, we had seen how to do stability analysis when the system was more than one dimensional. So we had studied basically two-dimensional linear systems, and we had seen what kind of fixed points or stable points can arise in those systems and how to classify their stability. So for example, we had seen examples of stable nodes and unstable nodes. Then there were examples where we had spirals which were stable and unstable, and then we had also seen examples of saddle points. And then we had also seen examples of other kinds of fixed points like degenerate nodes and stars and so on. So we saw that the stability of these various kinds of equilibria or fixed points could be analyzed by studying the eigenvalues of the determinant matrix, eigenvalues of the matrix equation, right? So the linear system we had was of the form x dot equal to a into x, where x represents the vector in the 2D plane, and we had an equation like this. So the linear system always had a fixed point at the origin, and basically the eigenvalues of the matrix A, which were lambda 1 and lambda 2, they go on to determine whether what type of equilibrium we get from these systems. Using the trace and determinant of this matrix A, one can classify the fixed points into various types, as I had mentioned earlier. And then we had also done certain examples regarding of such two-dimensional linear systems. So in this lecture, we will start studying nonlinear systems, two-dimensional nonlinear systems for the first time in this course. Okay, so the two-dimensional nonlinear system is basically given by an equation like this. Okay, so you have, I say that x is a vector because now it is in 2D instead of 1D. And then you have something which goes like, which is a function of x. Okay, so f can be a linear function or a non-linear function. Okay, so basically, if my x vector is denoted by coordinates x1 and x2, then basically we have something like x1 not equal to f1 as a function of x1 and x2, and x2 dot as a function of x1 and x2. So this vector x, it represents a point in the two-dimensional phase space. So here the phase space, as we had seen in the previous class, is given by basically the two coordinates or the two quantities x1 and x2. And so each point in the phase space denotes the vector x like this. Okay, and then you can map the trajectory of the points. So suppose x naught is the initial location of the point and it goes around the phase space somewhere like this. So you would get this trajectory once you are able to solve this differential equation. All right. So x of t represents any instantaneous location of a point along the trajectory. And similarly, in nonlinear systems also, you can have fixed points, you can have closed orbits, and so on and so forth. But now the question is, how can we analyze such a system? So for a linear system, it was easy, but the nonlinear system, it cannot be solved exactly because the right-hand side cannot always be written in terms of this particular equation, right? Because this is possible only for linear system. So what we do for a nonlinear system is that we make some approximations like the linear stability analysis, which we had seen earlier for a one-dimensional systems. Okay, but before that, let us take an example and see whether we can actually get insights into the phase portrait of a nonlinear system without going into linear stability analysis. So suppose you consider a system like this where x dot equal to x plus e to the power minus y and y dot equal to minus y. So how would the trajectories of in the phase space of the system would look like? So the first thing which one tries to extract from such systems are what are known as null planes. What are null planes? Null planes are basically the lines along which either x dot equal to 0 or y dot equal to 0. So x dot equal to 0 basically refers to the x null plane, meaning that there is no flow in the x direction along that null plane, while the y dot equal to 0 represents a y null plane. So if you look at this system, the y null plane, it is basically given by the y equal to 0 line. Okay, so that means along this line, y dot equal to 0, that means flow is parallel to x-axis, right? Okay, and the other null plane is given by x dot equal to 0, which basically implies that e to the power minus y equal to minus x. So this is the other null plane. So along this null plane, what happens is that along this x dot equal to 0. And what are the fixed points of the system? You see that the fixed point of the system is given by y star equal to 0, which basically means that x star equal to minus 1. So this is the only fixed point of the system. So now let us take a look at what the phase portrait would look like. So the fixed point is at minus 1 comma 0. We still do not know whether it's a stable or an unstable fixed point. Now let us see what happens as time goes to infinity. Okay. So if you look at the y equation, some constant c into, so it is a, can call the constant by 0. So it is a universally decaying solution. So basically the solutions all tend to approach the line y equal to 0 as x t goes to infinity. So basically all the solutions will try to approach the x-axis, right? And as y goes to 0, what happens is that to the power minus y, it will go to 1. So when that happens, then the right hand side of the x dot equation, then x dot tends to approach this line, x plus 1. All right. So the flow along the x-axis, so the flow along the x-axis is governed strictly by the line. Sorry. Just hold on. Hello. Uh, Sorry for the interruption. So the flow along the x-axis, as I was saying, is governed along the x direction is governed by this particular equation. Okay. So at late times when the solution approaches this line y equal to 0, then the direction of the flow of the solution depends on this. So you see that x plus 1, this is less than 0 if x is less than minus 1, and this is greater than 0 if x is greater than minus 1, right? So this basically tells me that the flow along the x-axis will be in this particular direction. So therefore, since the flow is away from the fixed point over here, this tells me that the fixed point is an unstable fixed point. Okay. Similarly, so we saw that one of the null lines was x, this line given by y dot equal to 0, and the other null line is basically given by this equation that x plus e to the power minus y equal to 0. And this equation represents this particular line over here. So I'm drawing this dotted diagram just to denote the fact that this is not a trajectory but a line line. So along this curve, the solution is always in which direction? It is always in the vertical direction. Now, whether the solution is vertically upwards or vertically downwards, it will depend upon the sign of y. Okay, so let us write this equation that all right. So along this particular line, if if y is greater than 0, then what happens that y dot is less than 0. Therefore, the solution will be vertically downwards in this direction. And similarly, when y is negative, the solution is vertically upwards along this line. So this basically tells us that the flow would look somewhat like this. So it will come from the top like this, and it will tend to approach this direction like that. So it's one trajectory. Similarly, if you have a trajectory coming from below over here, it will try to go like that. And similarly, something coming from here would go like that. And a trajectory coming from here, it will just turn around and go like that. So this is a stable manifold, and the unstable manifold is basically given by this. So sorry, I mean this is a stable manifold. So the solutions along this will approach the origin. So the origin turns out to be an unstable fixed point. Okay, in fact, it turns out to be a saddle point. Now, as we saw in one-dimensional systems, there was an existence and uniqueness theorem. Similarly, in two-dimensional nonlinear systems also have an so what does this say? That if you have the initial value problem that x dot equal to f of x, and suppose that x at time t equal to 0 is given by the vector x0. Now, if is continuous and all its partial derivatives of at least first order are continuous or x belonging to some open connected set D of the set of real numbers, then or any x naught which belongs to the set D, the solution x of t exists on some time interval minus tau comma tau out equal to 0, and the solution of the existence and uniqueness theorem. Like in one dimension, we had seen that if the first order derivative was discontinuous within this interval, then the solution would be non-unique or it may not exist. So similar statement goes true for two-dimensional systems as well, where we have partial derivatives instead of total derivatives. So what do we mean by partial derivative? So if f is a function of x1 and x2, then the partial derivative of f with respect to x1 is given by this, and that of f with respect to the second variable x2 is given by this. Okay, so an important corollary of the existence and uniqueness theorem is that trajectories in phase space from different initial conditions cannot intersect. So if they would intersect, then the solution would become non-unique. So this has important topological consequences in two-dimensional phase spaces as opposed to other higher dimensional phase spaces. For example, if there is a closed orbit in the phase plane, for example, if there is a closed trajectory, you can have trajectories like this in the phase plane, which we call C. Then any trajectory starting inside C would remain trapped in C forever, right? Because if it were trying to exist, if it would try to escape from this closed space, then it will basically intersect the trajectory C, and that will violate the existence and uniqueness theorem. So this is an important theorem which we will come across in this one also follows from another important theorem which we will come across in the next class, which is known as the Poincare-Bendixson theorem, which states that if a trajectory is confined to a closed bounded region and there are no fixed points in that region, then the trajectory must eventually approach a closed orbit. So we'll see this thing later. But for the moment, let us see how we can do stability analysis for nonlinear systems. Okay. So we do something which is similar to what we did in 1D, and that is linearization. So let us consider the two-dimensional system. And say that y star is a fixed point for this system. So f of okay. Now let us consider a small perturbation around the fixed point. So suppose the x component of the perturbation is u, which we write as x minus x star, and the y component we denote as v, which we write as y minus y star. Now we have to see whether the perturbation grows or decays. So if the perturbation would decay, it would be a stable fixed point. And if the perturbation would grow, it will be an unstable fixed point or a repeller. So we have u dot equal to x dot and v dot equal to y dot as a consequence of this. Now we do a Taylor series expansion of the function f about the fixed point. So a two-dimensional Taylor series expansion, therefore we have partial derivatives instead of full derivatives, right? Sorry, this will be x plus e L f plus higher order terms. So you can have del 2 f del u, which has a coefficient of u square. You can have del 2 f del y square, which has a coefficient of v square. And you can also have cross derivatives like del f del x del y, which has a coefficient of u. So we call these the higher order terms. Now, since this quantity is zero, we have this is equal to x plus v del f del y plus higher order terms. Okay, now you see that the left hand side, that is f of x star plus u and y star plus v, that is nothing but x dot or v dot, right? So this quantity is nothing but x dot because x dot is given by f. So basically we have this is nothing but u dot. Similarly, one can find v dot, which will be given by plus yes, same with higher order terms. So therefore, we can write these two equations together in terms of a single matrix equation. Yeah. Into sorry to UV plus higher order terms, right? So we can neglect the higher order terms at first approximation. And if you do that, then you see that this matrix equation, this has the form of the two-dimensional linear systems which we were analyzing earlier. So this has this particular form, right? So basically, about a fixed point, one can approximate um, about a fixed point, one can approximate a nonlinear system as a linear system in order to find its stability. And the stability can be basically obtained by evaluating the eigenvalues of this matrix, and the direction and the eigendirections basically they tell us about the ways in which the flow around the fixed point can behave. All right, but one thing that needs to be made sure is that one this analysis would only hold true if u and v are very small. That means only we are in some very small neighborhood of the fixed point and not away from it. So hold on a moment while the internet comes back on. All right. So this is what we, so the matrix A, we basically call it the Jacobian matrix. So A is given by so this is what we call the Jacobian matrix. And the eigenvalues and eigenvectors of the Jacobian matrix are what end up determining the stability of the system. Basically, the eigenvalues determine the stability, and the eigenvectors, they tell us how the flow behaves near the fixed point. Okay, so now let us take a look at a few examples of linearizing a nonlinear system and how we can classify their fixed points. Okay, so we begin with a small example. So one can consider the system like this. Say x dot equal to minus x plus x is cube and y dot equal to minus 2y. Hello. So the system is an uncoupled system, and the fixed points of the system are basically given by y star equal to 0. And from the x dot equation, there are two other fixed points which come up. Those are basically solutions to this equation. So fixed points are plus, minus 1 and 0. So there are three fixed points of the system, which are minus 1, 0, um, 0, 0, and 1, 0. And all three fixed points are along the x-axis. And the Jacobian matrix, which is matrix A, as you said, this is what it should look like. So del f del x is basically minus 1 plus del f del y is 0, del g del x is 0, and 2. Okay, so we have to evaluate the matrix at all fixed points. So for 0, 0, we have the matrix A is given by minus 1, 0, 0, and minus 2. So here the trace of A is tau, which is minus 3, and determinant of matrix A, which is delta, that is equal to plus 2, and tau square minus 4 delta is equal to 9 minus 8, which is equal to 1, which is greater than 0. So the fixed point at the origin, it is a stable node. Similarly, so this part of the analysis, if you remember the previous class, this comes from the linear stability analysis, which we had done in the previous lecture. So this tells us that the origin is a stable node. Similarly, if you look at the plus 10 and minus 10 point, both have the same matrix. So plus minus 1, 0 matrix C is given by 2, 0, 0, 2, minus 2. Right. So again we have the trace is 0 and the determinant is equal to -4, and this basically implies that the points plus minus 1 are saddle points. So what would the phase portrait look like? So if they are saddle points, then they should have a stable eigendirection and an unstable eigendirection. How to find out these directions? We have to solve the equation for this point at so what are the eigenvalues of matrix A? The eigenvalues of matrix A are given by the equation 2 minus lambda into 2 plus lambda equal to 0. So the eigenvalues are lambda plus minus 2. And therefore, so for the lambda equal to 2 eigenvalue, we have the eigenvector equation so this is V1 minus 22, right? So this implies that equal to 0, which implies that the eigenvector V1 is basically given by 1, 0. So this is the unstable eigendirection. So the unstable eigendirection is along the x-axis, and similarly, if you look at the stable eigendirection, it will turn out to be the stable. So the stable eigendirection is along the y-axis. Therefore, the phase portrait of the system would look as follows. So if this is x and this is y, the origin is a stable fixed point. The unstable fixed point is at minus 1, 0 and plus 1, 0. And we saw that the stable eigendirections and the unstable eigendirections were along the y-axis, right? So y-axis had the stable eigendirection, and this was the unstable direction. So what do the trajectories look like? So any trajectory starting from here would go like this and hit the fixed point at the origin. So starting from here would go and hit like that. Something like this. You will also have to reflect like this from the top. And all the trajectories, if you're starting on the other side of the stable manifold, they would go up to infinity like this. So in this way, we are able to map out the phase portrait of the entire nonlinear system. We can also take a look at another example So another example of a system is that just hold on a second. So we can consider now a coupled system. We had initially an uncoupled system. X dot equal to so what are the fixed points of this system? Fixed points of this is given by so another thing which we observe is that this is the equation of the x plane. So along this line, the flow is so along this line x dot equal to 0, the flow is completely vertical. That means it's in the right direction. So now we substitute the value of x over here. And corresponding to these values, what will x be? X equal to y cubed by 4, which is 0 plus minus 2 cubed is 8, so 8 by 4 will be 2. So the fixed points of the system are 0, 0, 2, 2 and minus 2, minus 2. And one interesting thing which you can note from this equation is that, actually I'll come to that later, but before that, let us classify the stabilities of the fixed points. So the Jacobian matrix, which is A, is basically given by here is equal to y cube minus 4x and g is equal to y cube minus y minus 3x. Sorry, I think the screen sharing might have stopped for some time. So Okay, so my screen sharing had stopped somehow by mistake, so I would have to do this problem again, I think. So yeah, so by the way, for doing this problem, one interesting observation is that um, x dot is equal to y dot when x equal to y for this system, and this can be simply obtained if you equate the two equations. You see x dot equal to y dot, then this is the equation that you get. Alright, so this basically means that if a flow starts along the line x equal to y, it will always stay on the line. Okay, so this line is basically what is known as an invariant of the flow. So this is another new terminology that we come across in this term. So yeah, so again we basically have to find the fixed points. So y cube x should be equal to y cube by 4 for the fixed point, and if you substitute x equal to y cube by 4 into this equation, then what you end up getting is that y into y square minus 4 is 0. This gives us y equal to 0 and plus minus 2. Corresponding to this, we have x equal to, from this thing, plus minus 2. Therefore, the fixed points of the system are 0, 0, 2, 2, and minus 2, minus 2. So these are the three fixed points of the system. Okay, now coming to the Jacobian matrix, which is given by so we evaluate the Jacobian matrix with f equal to cube minus 4x and g equal to minus 5 minus 3x. So basically, then the matrix A is basically given by delta x would be minus 4. So we have to evaluate the matrix A at the different fixed points. Okay. So for the fixed point at the origin, which is 0, 0, find that the matrix A is given by minus 4, 0, minus 3, minus 1. Alright. So the face of the matrix is given by minus 5. Determinant delta is equal to 4. Right. So then tau square minus 4 delta is nothing but 25 minus 16, which is 9, 0 and 0. Therefore, this is positive. So the origin is a stable node, like we saw in the previous example. Okay, now let us take a look at the other one, 2, 2, in fact for and also for -2 again, because there is x square, there is only y square over there, so plus 2 and -2 will have the same Jacobian matrix. Alright, so for this answer to be -4, 4 into 3, 12, -3, 12 minus 1, 11. So therefore we have r is equal to 7 and delta is equal to so r is equal to 7 and delta is equal to -44 plus 36 minus 8 is less than 0. Therefore these are basically saddle points. Okay. Now we can also compute the stable and unstable eigendirections for these 2 points. So they turn out to be, first you have to find the eigenvalues of this matrix equation for that matter. So the eigenvalues are basically given by the solutions to the equation. So these are the 2 eigenvalues corresponding to the stable, unstable and stable directions. Yeah, there are 2 eigenvalues corresponding to the stable and unstable directions. You can find out the eigenvectors. So if 1 corresponds to 1 equal to -1, stable 1. So for this we have so the eigenvector v1 corresponds to any vector like 1/4 and the eigenvector of the v2 corresponds to lambda equal to plus 8, which is the unstable one. Alright, so for this we have allowing it to 1% to be something like 4 comma 1, and similarly the other one corresponds to this table 1. So this is C, unstable as a direction. So if let us try to draw the face portrait now. We cannot be sure that we'll be able to draw the entire one, but this we can try. So the origin is the stable node, as we saw, and the unstable fixed points are present at plus. So saddle point is 2. Okay, and the stable eigen, the unstable eigendirection, or the stable eigendirection, which corresponds to this eigenvalue, is basically given by 4 comma 1. So this basically corresponds to something like this. So stable eigendirection, and the unstable one basically corresponds to 1 comma 1. This is the unstable eigendirection. Here we do not draw the lines all the way to infinity because linearization applies only in the neighborhood of these fixed points. So in the neighborhood of these fixed points, the flow is like this. and this is like corresponding to x equal to y. So this is the invariant one. So the flow that remains close to the side always stays to this as t goes to infinity. Now we will see the effect that the small nonlinear terms can have on different kinds of fixed points. Okay, so we saw in the previous class that the centers and stars, all these are not robust fixed points. So the robust fixed points are the attractors and the repellers, while the others were basically borderline bases. So any small perturbation to a center can change it into either an attractor or a repeller. For example, small nonlinear terms can change a center into a spiral. So that is what we will see from the next example that we consider. So in the previous example over here, if you basically find out the null points of the system, and the null points are basically given by equations where x dot equal to 0 and y dot equal to 0, then you will be able to map out the phase portrait of the system to some extent. Okay, so I didn't show that over here, but it is possible to do it. Okay, now let us consider the system x dot equal to this y plus center which is equal to y square and y dot equal to x plus y into x square plus y square. Now if you try to linearize the system, then what we do is that we basically neglect all nonlinear terms. So if you try to linearize the system, then the linearized system becomes x dot equal to minus y and y dot equal to x. So the fixed point is again given by the addition, and the Jacobian matrix at the fixed point, it looks like 0 minus 1 1 0. So over here the phase is 0 and determinant is plus 1, so which is greater than 0. So linearization predicts that 0 0 is S by center. So this is what linearization will predict. But now we will see that, but what did we do in a linearized system? We basically neglected the nonlinear terms. But now you see that this is actually incorrect, because if you include the effect of the nonlinear terms, then it becomes something different. So to analyze a nonlinear system correctly, what we do is that we make a change of variables. Okay. Right. So the change of variables would be as follows. So you consider x as r cos theta and y as r sin theta. So then we have x square plus y square is equal to r square, and x dot plus y dot is equal to r dot. This directly follows from this equation. So if you substitute the values of x dot and y dot from the original system, what you get is that r dot is equal to x into so finally we get call this equation 1. Similarly for theta dot, we have this can be derived from our definitions of x and y. And if you do that and substitute the values of x dot and y dot, you obtain theta dot equal to 1. So you see equations 1 and 2, they give me a dynamical system in terms of the polar coordinates r and theta, right? So the new dynamical system is basically r dot equal to ar cube and theta dot equal to 1. Now the fixed point of this dynamical system is given by r star equal to 0. So basically this implies that the origin is a fixed point. Now if you see that if a less than 1, then basically r dot is negative. This implies that starting from a finite radius, where if you start from r0 equal to r at t equal to 0, then the solution of the r dot equation will gradually decay towards the origin, that is r equal to 0. So what does the trajectory of the system look like in that case? So if you look in the plane of x and y for a less than 1, then you start from a finite radius like this. The radius will continue decreasing as the system spirals toward the origin, and then it will hit the origin like this. So you get a, what do you get? You get a stable spiral. Similarly, when a is greater than 0, then the value of r continues to grow indefinitely. So if you start from here, then basically you will spiral further and further away from the origin. Alright. So this is for a greater than 1. You get an unstable spiral. And Finally, when a is equal to 0, then r dot is 0, that means the radius does not change. So this gives me closed trajectories like this for different values of the initial radius r. So you saw that whereas the linear stability analysis predicted the origin to be a spiral, nonlinear terms can make the origin, can change the stability of the origin and give us, but the linear stability analysis predicted the origin to be a center. The presence of the nonlinear terms changes the nature of the fixed point, and we actually see that the fixed point turns out to be a spiral. So the spiral is stable when a is less than 0, and the spiral is unstable when a is greater than 0. And this happens because we now try to look at what happens away from the fixed point. Okay? So the close to the fixed point, you would see that the dynamics of r dot equation, r is very small, right? So close to the fixed point, you might approximate r dot to be equal to 0 because r is small, and therefore it might, and since linearization only applies to when we are very close to the fixed point, it therefore predicts the origin to be a center because it by default assumes that r dot equal to 0. Okay. So the takeaway message from this section is that nonlinear terms do end up changing the stability of fixed points, and the linear stability analysis only applies if we are extremely close to the fixed point. Okay. So the marginal cases, what happens is that um, one thing to note is that the stability of the stars and degenerate nodes cannot be altered by nonlinearities. Okay. Like for example, centers are basically neutrally stable fixed points, so the nonlinearities can alter their stability itself. But if you look at stars and degenerate nodes, they can either be stable or unstable. So a star can be converted into a node, stable or unstable node by the nonlinear terms, but its stability remains the same. Its stability does not change. Okay. So now let us take a break of 2 minutes. After the break, we will see a real world example of a two-dimensional nonlinear system, and we will try to draw certain insights from that. Hello. So there is a slight change in plan. Um, so before we start discussing the population dynamics, there are two things I would like to mention. So discussing population dynamics will take time, so we'll do that in the next class. First thing which I would like to talk about is this problem which I've shown over here. So we had made a slight mistake over here. I'll correct the mistake right now. So basically the face portrait should look like this. So this was the stable fixed point, and there were unstable fixed points along the line x equal to y. And we saw that for both these cases, the stable eigendirection for the saddle points, the stable eigendirection was this, stable, and the unstable eigendirection was spanned by this vector. Okay. So the unstable eigendirection is basically spanned by the line x equal to y. So this is the unstable direction, and this is the stable direction. Similarly, for this point also, the unstable direction is this, and the stable direction is the same, like this. So you see that all the trajectories, they approach the origin along this line, x equal to y. So any trajectory along the line is equal to y would approach the origin like this, right? And any trajectory along the line x equal to y, which lies on the other side of the fixed point, will go up to infinity. This is x and this is y. Now, if you look at the origin, let us take a look at the matrix corresponding to the origin, the Jacobian matrix. So the what was the matrix we had over there? So the origin corresponding to this: -4, 0, -3, -1. -4, 0, -3, -1. So the eigenvalues corresponding to this matrix are basically given by lambda equal to -4 and -1. Okay. So what are the eigenvectors corresponding to these eigenvalues? They turn out to be. So first I look at the smaller eigenvalue, which is lambda equal to, or the slower eigendirection, one of the smaller denomination. So over here it turns out that -4v1 is equal to -v1, implying that v1 equal to 0. So therefore the eigenvalue corresponding to eigenvector corresponding to the eigenvalue lambda equal to -1 is basically 0, 1. So this is the slower eigendirection, right? And the faster eigendirection, it is given by the eigenvector corresponding to lambda equal to -4. So that is basically -4v1 and -4v2. Alright, so we have again -v1 -v2 is equal to -4v2, right? So that implies that v1 equal to v2. So this is the eigenvector which is corresponds to the faster eigendirection. So if you look at these vectors, so the faster eigendirection basically corresponds with the line x equal to y, and the slower eigendirection is corresponding to the line 0, 1, which is this. So the y-axis is the slower eigendirection. So what happens is that all these trajectories they would try to become parallel to the y-axis as they approach the origin. Right. So basically you will have trajectories approaching the origin like this. And so on and so forth. So yeah, this gives us the somewhat of a qualitative picture of the phase portrait. So that was what I wanted to say about that problem. Now, uh, instead of doing the population dynamics, there is something else which we can talk about, and that is conservative systems. So conservative systems are basically the systems in which the energy is conserved. That means you can define a quantity such that its time evolution is equal to 0. So for example, the simplest example of a conservative system which one can think of is an undamped pendulum. Okay. So an undamped pendulum, in the absence of friction, it does not dissipate energy, so its energy remains conserved. Now the equation of a, how do we derive the equations for a conservative system? We know that the equation of a mass moving in one dimension is basically given by mx double dot equal to f of x, and the force can be written as a gradient of a potential, right? So we consider only one dimensional systems here for the time being. Therefore, the force can be written in this manner. Then we have mx double dot plus dv dx equals to 0. So this is an example of a conservative system where capital V is the potential energy of the system. Now, how do we define the total energy? What we do is that we multiply both sides of this equation by x dot. So you have m x dot x double dot plus x dot dv dx equal to 0. So this is basically ddt of x dot square. This is the first term, and the second term, by chain rule, we can write the second term as ddt of v of x. So this comes about by chain rule, and if you do that, we get dt of half So you see, you are able to define a quantity which you can refer to as E. In many cases, this is what is known as the total energy. So the quantity E, it is invariant along the trajectories. That means its time derivative is equal to 0. It is a constant along all trajectories. And therefore, this is what defines a conservative system. So let us take a look at an example of a conservative system. So suppose, and how its trajectories look like. So suppose, for example, you consider the potential Vx to have the form of then the equation of motion can be written as this turns out to be. So this can be written as a coupled as two coupled first order systems x minus x squared, where y is basically the velocity of the particle, which is x dot. So we have studied a similar system previously. So the fixed points of the system, fixed points are basically given by 0, 0, um, 1, 0, and minus 1, 0. And to classify the fixed points, we okay, that part is gone. So I would basically start off with the information which I had. So the Jacobian matrix is given as 0, 1, 1 minus 3x squared, 0. So it's a trace. So you have to evaluate it at the different fixed points. So if we first consider the origin, turns out to be trace is 0, and the determinant is equal to minus 1. Therefore, it is a saddle. And for the other fixed points at plus minus 1 comma 0, we have the trace equal to 0, and the determinant is given by 1 minus 1 plus 2, so that is equal to 2. So the other points are basically centers. So now we see that the origin is a saddle and the other fixed points are centers. But we had seen earlier that nonlinear terms can actually perturb the centers and destroy them into stable or unstable fixed points. And this center which we get, it is predicted by linear stability analysis, which basically ignores the nonlinear terms. And we had seen that the nonlinear terms can convert a center into a stable or unstable fixed point, right? But here the thing is that the energy is conserved here. Therefore, because the energy is conserved along trajectories, the trajectories along the origin turn out to be all closed curves. Okay, so if a stable or an unstable spiral can only occur if the energy of the system is not conserved. So for example, if you have a stable spiral, then you have the system converging towards a fixed point. And as it does so, it dissipates energy. Similarly, if you have an unstable spiral, then the system goes away from the fixed point, and as it does so, it gains energy. But here, the system is a conservative system. And since it does not gain or lose any energy, so the trajectories will have to be closed paths which circle around the center. Okay, so only along closed paths will energy be conserved. Therefore, the center does not lose its stability if the system is conservative. So this is an important point one should make note of. And so if that is the case, then the phase portrait of the system would look somewhat like this. So before doing the phase portrait, since we saw the origin was a saddle point, it is better to first find the stable and unstable eigendirections corresponding to the origin. So the eigenvalues are basically given by lambda square minus 1 is equal to 0. Lambda is plus minus 1. So if v1 corresponds to lambda equal to 1, then we have 0, 1, 0, v2 is v2. So this implies that v1 equal to v2, which tells me that the eigenvector corresponding to the unstable direction is this. And the eigenvector corresponding to the stable direction is and so this turns out to be this is a stable eigendirection. This portrait would look as follows. So here you have the center, here you have the center, and here you have the saddle. Okay. So for the saddle, this is the unstable direction, and this is a stable direction. Alright. And these are basically centers, so the trajectories will go around them like this. But what is the direction? So when this situation happens, then you see that as you come closer and closer, the trajectories do not become oblique spirals, but they keep on going around like this. So this is the direction of the rotation. And these trajectories, they come around like this and close in on themselves, because we saw that the system is conservative, so the trajectory should come and close around themselves like this. The trajectories that close around themselves like that. And beyond this, what happens is that you have a trajectory which goes like that. So this gives us a roughly picture of the phase portrait. So this particular trajectory which passes through the origin, that is somewhat between the larger closed path and the smaller. So you see there are small oscillations above deep centers, and there are large oscillations which encompass both centers, and in between them there is a borderline trajectory which passes through the origin and again comes back and gets settled into it. So this trajectory goes on like that, and it comes back and sits at the origin. So along these trajectories, the oscillation somewhat gets stopped, and these correspond to the homoclinic orbits. So homoclinic orbits are basically the trajectories which approach the origin as time tends to homogenic orbits. So they approach the same fixed point as t goes to plus minus infinity. As t goes to plus minus infinity. Note that it does not correspond to a periodic solution because the trajectory takes infinite time in trying to reach the fixed point. Okay, because of the critical slowing down towards the fixed point. And such homogenic orbits are quite common in conservative systems, but in distributed systems they are very rare. And so if you look at it from the potential perspective, so if you try to draw the potential well for the system, so the potential basically looks somewhat like this. Okay. So the small orbits about the centers, so these are basically the centers, and the origin, this is the saddle point. So around the center they perform small oscillations like that, right? About this center also they can perform small oscillations which go around like that, and as the oscillation amplitude increases they keep on performing these oscillations until the point that the oscillation amplitude becomes so high that the trajectory starting from here just about reaches up to this maximum over here. And this maxima basically, this orbit basically where the trajectory oscillates and reaches just above the maxima, this corresponds to the homogenic orbit. And when you start off from here, then you see that the trajectories of this will go like that. It will cover the entire potential well, and then it will come back downhill like that. So this corresponds to the larger oscillations which go out all around the center. So this is what a conservative system typically looks like. I mean, there can be other forms of the potential V which can give different kinds of orbits and hence other different properties. But the most important thing that we learned about conservative systems for these examples is that because the system conserves energy, it cannot have a continuously decaying or continuously increasing solution. All the solutions will have to be closed curve because the energy is conserved along these closed curves as well. Okay, so the energy constant, the total energy, which is the kinetic plus the potential energy, is constant along each of these trajectories which I have shown in this case portrait. That is why the center is a robust fixed point when it comes to conservative systems, where the nonlinear terms does not destroy the center. So that is all from today's lecture. In the next lecture, we will study population dynamics and other interesting chaotic systems in two dimensions, and then we will move on to limit cycles and bifurcations in 2D.